Welcome to this explainer. Picture this for a second. You're peering into the layout of a modern VLSI circuit. You aren't just looking at a couple of wires and nodes, you're staring down at this insane, intricate metropolis packing millions, maybe even billions of individual transistors. The sheer scale of it is absolutely staggering. If you were tasked with analyzing how a signal travels through that, and you tried to calculate the behavior of every single transistor one by one, man, that would take lifetimes, and a completely unreasonable amount of coffee. So how on earth do we actually conquer this kind of complexity? Well, today, we're unpacking the elegant mathematical shortcuts engineers use to tame all that chaos, specifically Z, Y, and X parameters.
So really, how do we analyze these complex VLSI circuits without checking every single component? Think about that. If a traditional linear node-by-node approach is literally impossible, there just has to be a way to step back. We have to stop staring at the individual trees and start looking at the forest. And the answer? It lies in abstracting those incredibly complex internal components into a highly simplified behavioral model.
Here is our roadmap for this explainer. We're going to start with the two-port network solution. Then we'll cover Z parameters, Y parameters, and X parameters. After that, we'll compare all three to see exactly how they differ, and finally, we'll wrap up with why this actually matters in VLSI design.
Part 1. The two-port network solution. Let's dive right into this first concept.
Okay, here's the magic trick for simplifying all that chaos. Instead of analyzing hundreds of tiny internal components, we literally just draw a box around a specific chunk of the circuit. We call this a two-port network. Port 1 is your input side, and port 2 is your output side. And just like that, we only care about four things: the input voltage and current, V1 and I1, and the output voltage and current, V2 and I2. If we can nail down the relationship between these four variables, we know exactly what that complex block of circuitry is doing without needing to know a thing about what's actually inside the box.
Moving on to part 2, Z parameters, or what we can call the impedance lens.
For any traditional network analysis, Z parameters are totally foundational. Z stands for impedance, and it's measured in ohms. In plain English, Z parameters describe how the voltages in our two-port network respond to currents. The core math here boils down to a matrix where voltage simply equals Z times current. So, if you know the currents entering and leaving the network, and you've got your Z parameters, you can easily calculate both of your port voltages.
Now here's a really important question. What do these parameters represent in the physical world? Let's say you're calculating Z11, which is input voltage divided by input current. The math requires that I2 equals 0. But what does I2 equaling 0 actually mean for an engineer sitting at a test bench? It means absolutely no current is flowing out of port 2. Physically, the output port is open-circuited. So Z11 simply represents the input impedance of the network when the output is left completely open. And this brilliantly illustrates the crosstalk between the ports. Take a look at Z12 and Z21. Z12 tells us how a current applied way over at the output port reaches back and messes with the voltage at the input port. On the flip side, Z21 tells us how the input current influences the output voltage. That Z21 parameter is incredibly fascinating because it essentially describes the forward transfer characteristic, which is absolutely vital when you're analyzing how amplifiers and transistor circuits push signals forward.
Part 3. Y parameters, the admittance lens. Now that we've got a handle on impedance, let's totally flip the script. Enter Y parameters. Y stands for admittance, and the unit here is Siemens. Mathematically speaking, Y is just 1 divided by Z. It's the inverse. So, while Z parameters describe how voltages respond to currents, Y parameters describe how currents respond to voltages. And because it's the inverse, the way we physically find these parameters flips too. To find Y11, the equation says V2 has to equal 0. In the real world, unlike Z, where the port was open, V2 equaling 0 means the output port is hard short-circuited to ground.
So you're probably wondering, why do we even need both? Well, Y parameters are an absolute lifesaver in analog VLSI circuits. Think about a standard common source MOSFET working as an amplifier. If you look at a small signal model, its transconductance, or GM, basically tells us how much the drain current changes when we tweak the gate voltage. That is, by definition, a voltage-to-current relationship. Plus, at high frequencies, the tiny parasitic capacitances inside the transistor, like CGS and CGD, create these frequency-dependent admittances. So using Y parameters to analyze high-frequency MOSFETs isn't just nice, it's wonderfully convenient. Let's lock this in with a really quick memory trick. Z parameters are impedance, voltage over current, ohms. Y parameters are admittance, current over voltage, Siemens. Just remember, Z is V over I, and Y is I over V. Keep that fundamental difference straight in your head because it dictates exactly which mathematical tool you pull out of your toolbox when you're analyzing a circuit.
Part 4. X parameters and nonlinear RF behavior. Time to look at something a bit more modern.
Z and Y parameters are fantastic, no doubt about it. But they share one really major limitation. They assume small signal linear behavior. If you've got a transistor running a tiny input signal, sure, you can approximate it as a linear device. But what happens if you absolutely blast that transistor with a massive radio frequency signal? The device gets slammed into its nonlinear region. Those clean, simple linear models of Z and Y completely fall apart. And that is exactly where X parameters step in. They were specifically developed to characterize this chaotic, large-signal, nonlinear behavior. Here's what that nonlinearity actually looks like on a test bench. Say you feed a 10 GHz signal into a perfectly linear amplifier. You'd expect a larger 10 GHz signal out. Easy. But real RF transistors are far from perfect. When you push them hard, they distort. You put 10 GHz in, and your output will definitely have that primary 10 GHz signal, but it's also going to spew out harmonics at 20 GHz, 30 GHz, and so on. X parameters are designed to mathematically map out these complex wave relationships and harmonics that Z and Y parameters literally cannot see.
Part 5. Comparing Z, Y, and X. Let's put these three head-to-head. All right, this is the core takeaway of our whole explainer today, understanding the distinct differences between these three parameter sets. First up is Z. It represents impedance, the relationship is voltage divided by current, and it's your baseline for traditional network analysis. Next is Y. It represents admittance, current divided by voltage. This is your go-to for analog circuit design and small signal transistor modeling. Finally, you have X. It represents nonlinear RF behavior, looking at large signal wave relationships rather than simple V over I ratios. You use X parameters for RF and millimeter wave circuits where distortion and harmonics are huge factors. They are three highly distinct tools, each engineered for a very specific job.
Finally, Part 6, why this matters in VLSI. Let's ground all this abstract math into physical reality.
Look, if you're a VLSI layout engineer, you might be thinking, hey, I just draw polygons and route wires. Why do I care about a two-port network? Well, because your layout doesn't exist in a vacuum. When you draw two metal lines close to each other, you inadvertently create capacitive coupling between them. When a voltage signal switches on line A, that changing voltage injects a current right into line B. Boom, you've got crosstalk. You might just see two metal routes on a screen, but electrically, you just built a two-port network full of parasitic resistance and capacitance. Network analysis is the language we use to figure out what your layout is actually doing.
And that brings us to this classic, unavoidable approximation, 0.69 RC. If a long interconnect wire in your layout has resistance R and capacitance C, the signal delay across that wire is going to be roughly 0.69 times R times C. It's an inescapable physical reality. More resistance, more delay. More capacitance, more delay. You can't cheat physics. The parasitic elements you accidentally create during physical layout directly throttle the speed and performance of the final chip. Network parameters, especially Z and Y, are how we quantify, model, and ultimately fix those parasitic delays long before a chip ever hits the foundry. I want to wrap up with a thought straight from our source material. So whenever you see a complicated VLSI circuit, don't always think about every transistor individually. Think of it as a network, understand its ports, understand its parameters, and then analyze how voltage, current, impedance, admittance, and frequency interact. That is the power of network analysis in VLSI. The next time you glance at a hopelessly dense circuit layout, will you just see a billion confusing transistors, or will you see an elegant network just waiting to be solved? And honestly, as we push further into sub-nanometer nodes, you really have to wonder, are Z, Y, and X parameters going to be enough to model the quantum weirdness of tomorrow's chips? Thanks for joining me for this explainer, and keep exploring.